let me briefly review what we learned last week. So first, forward rate, small t, big T, T plus delta T. The meaning of this forward rate is value of $1 at time big T. No, actually, sorry. Is a value of a contract. This is basically value of a contract at time big T that pays $1 at big T plus delta. Okay. So $1 happens at big T plus delta. And the price of that contract at time big T is determined as small t today. Okay. The actual contract is big T. Okay. So we already learned this for the price. So for the price, F small t, big T plus delta T is basically it is the long run lending and short term borrowing basically. So it is a ratio of two zero coupon mode price, ZT big T plus delta over ZTT. Again, this is value of $1. Now value of a contract that pays $1 at big T plus delta as small t, and the denominator, this is the value of $1, value of the contract that pays $1 at time big T as small t. And then if we use forward rate, basically we can express forward price as exponential of forward rate, and then to normalize time, we multiply delta over here, time difference, because we want to annualize. So to use this last two parts, okay, to use this last two parts, we can solve small ft, small f forward rate. So if we solve f, then we can get rid of minus. Then we change the denominator, denominator, and take log. And then divide by delta. Then we have this forward rate. So forward rate is log z t big T minus log z t big T plus delta over delta. And then of course this forward rate changes over time. Okay. Because forward rate, today's forward price would be different from tomorrow's forward price. Therefore, today's forward rate we determine today would be different from tomorrow. So change of the forward rate from t to t plus dt. Dt can be very small time or like 1 month, 1 day, whatever. Is this one? This is not equal. Okay, it is equivalent. The definition. Okay. So we write down this way. Now we can do the coding. Okay. So we import modules. Okay. And then import numpy, import the matplotlib library as plt, and tabulate. And then we use style, Seaborn white gray, very flash graphic tool. Seaborn is a very flash graphic tool. Generally very pretty graph. N is 10, so it's number of data point per yield curve. So suppose we observe like 10 yield, 10 spot rate today. Okay, if we link spot rate, that is yield curve, right? So suppose we have 10 spot rate, yield curve that includes 10 spot rate. And then T is the time of those 10 spot rate, like which months we observe. And here delta, this one big delta, let's say it is 1 over 12. So it means per data point, the difference between the data point is 1 month. Okay. So we have for yield curve, of course, it is not that realistic. So it means we observe like next 10 months, we observe next 10 months of yield. Okay, because per period is 1 month and n is 10, right? If we of course make this one 12, then well, we observe next 1 year of data point, but we have 12 over here, 12 over here, so you might be confused. So I intentionally make it 10. Okay, and then just a moment. Okay, sorry. Let me continue. So we have setting now. Of course, ideally, we want to use real data, but since we don't have real data, therefore, I want to simulate the data. Okay, I want to simulate the data. So yeah, first I simulate what? I simulate zero coupon yield of zero coupon bond price, which is basically spot rate, right? So yeah, basically I did numpy cumulative sum of standard normal. I simulated because with 10 data point, I simulated 10 random number. It is NP random, so it is from uniform distribution. So it's not, it cannot be negative, and then divided by 1,000 to make it very small. And I did a cum sum, so it is added from the previous value. Okay, so this yield curve, JCB, YTM yield curve looks like, yeah, hold on. So JCB yield curve looks like this one. So plot JCB yield curve red dot line. So this red one upward sloping curve. Okay, yeah, so it is a simulated yield curve. And then of course zero coupon, since we have yield, now I can calculate zero coupon bond price. It is numpy of exponential zero coupon yield, and T. T is a segment, but per segment, here per segment, it is the 1 month. So I multiply delta over here. So T plus delta is like a time to the maturity. Okay. Since we have zero coupon bond price, now I can calculate for the price using the formula over here, right? This one. Yeah, this one. So yeah, like this one. I use very small small text. Very first for the price is same to zero coupon bond price, and from next one is 1, 2, and then 0, 2 minus. So basically I shifted one per data point. Okay, the first one same. And the forward rate is, of course, now we have this forward price. So here, so this is log. So well, so this is basically, as you can see, okay, this is basically the same too, right? Log where log forward price, well, minus, okay, okay, much better. Ah, this delta thing is, I'll make it this way. Okay, so it is the if we combine this log, the log of z over this one, but this is inverse of this f, so I put negative over here, right? So it's basically the same. So I use this part, to formulate, to calculate forward rate like this. And then again, dt is change of time. It is again 1 over 12. But suppose if we observe data daily, then like it is 222. If we observe data daily, okay. So here, let me make it 1 over 252. Number of business days per year, okay. And then next, tomorrow's zero coupon yield. Now I did the same thing again. So it is today's data. Now it is tomorrow's data. I simply simulated and tomorrow's zero coupon price. And now, of course, I will T plus DT over here, right? Right? No, I don't think I need a DT over here. So actually, I don't need this one. Okay, it shouldn't be over here. Okay. And then for the price, same tomorrow's forward rate. Now the D forward rate is tomorrow's forward rate minus today's forward rate, like this one. So I simulate data, and then I tabulate data so that I can see the tomorrow's forward rate, today's forward rate, and the change of forward rate. Okay, so print it like this. Let me run again because I changed the data. Oh, it is 0. Why is 0? It shouldn't be 0. It should be 0 because it should 1 over here. Okay. Yeah, the data is different. Okay. So it looks like this. So this is today's forward rate, tomorrow's forward rate, today's forward rate, and difference. So difference is change of forward rate. So I made a graph. So the red dotted line is the zero yield. And from zero yield, now this blue one is forward rate. So this forward rate, red one, so when red one increases, it increases. When slope decreases, it decreases. So it looks right. So here slope decreases, so yes, it drops. So that's fine. And then change green line looks like this. So everything looks fine. Okay. Okay, so this point we already learned. Now next we learn very important concept called forward rate. No, forward pricing kernel. The definition of pricing kernel. So in finance, the purpose of in financing we have field called asset pricing, and possibly many people say so. The whole point of asset pricing in finance, basically we have corporate finance and asset pricing. There are two primary fields. Of course, there are also market microstructure or other field, but corporate finance and asset pricing, basically corporate finance and investment theory, they are two primary subfield of finance. Okay, corporate finance and asset pricing. You learn asset pricing as an investment theory, 투자론. Okay, 재무관리 and 투자론. Okay, they are two primary fields, and 투자론 is asset pricing. And some people say the whole point of learning asset pricing is about pricing kernel, because price kernel determines asset price. So pricing kernel is basically random variable. Here I denoted pricing kernel as MT plus DT. So pricing kernel, as the name indicate, pricing kernel gives you price. Okay. So like NPV gives you price, right? Discounted cash flow. comparable firm. They all gives you fair price of some project or something. But in general, in finance, everything boils down to this pricing column. And the pricing column is basically, suppose we have tomorrow's cash flow, PT plus DT, and then it is possibly uncertain. So we only know the distribution of PT plus DT and multiply pricing column another random variable and take expectation of it. Then it is today's stock, today's price. So asset pricing is in some sense simple. Figure out distribution of tomorrow's cash flow P. Figure out distribution of the pricing column. Multiply it, get the average of it or mean of it, and then you have a price. Okay, and then we are fixed income class, bond class, and in bond, one very popular way of modeling this pricing column is affine term structure model. So affine term structure model is one particular way of modeling pricing column. And this affine term structure model, in affine term structure model, basically looks like this, but in this specific example, there are some variations of affine term structure model. But for the purpose of this class, I made affine term structure model. This is simple, actually not that simple, but like this. So now we have stochastic calculus in continuous time. Okay, so t plus dt is basically exponential of something. Exponential of risk-free rate first. It is natural. It is natural because we have to discount something in future with risk-free rate plus some risk premium. And then we have lambda t prime lambda over t dt part. This second term is called convexity adjustment term. And third term, lambda t prime dvt. Here, this part is important. Here, lambda t is called price of the risk. And then dz is Brownian motion, is called source of the risk. And then in the affine term structure model, we model lambda as a nu0, nu1 multiplied by some random variable nu t. Okay, to make it better, so let me add a bar. Okay, so we have a bar over here, slightly better. Okay, you need a bar, another bar over here. So here, bar. Okay, put bar over the one. Okay, so I have a bar because they are the constant. Okay, they are like given numbers, and nu t, this one I don't have bar, so it is like a varying random number, and I multiply delta to make those values independent of the length of the time data period for convenience. And this z nu t is basically stochastic term, something intuitively, it is something we cannot forecast in the process of this nu t part. Okay. And so here, so this one is this term is related with term, but out of this nu t, so it is like shock to the nu t. Some part of nu t we can forecast, some component of nu t we cannot forecast. So some the component of nu t that we cannot forecast, we denote that part as a dz nu t. And then this is variance covariance matrix of dz part. And if we multiply half of this covariance matrix, then we can normalize it into the standard Brownian motion. So for this part below, you have to know Brownian motion. And I assume you studied continuous part in my class video. Okay. So here, D nu T. So as I explained, D nu T is the source of risk. Therefore, since this is the source of the risk, the part I multiply this one, so this is called the price of risk. So possibly they are vector. So we have a multiple source of the risk. We can even include the big data. Then if we use big data, then we have a lot of source of risk. And this lambda t is a price of each source, a risk price of each source. And we multiply, right? And then our model is called Affine because the price of risk is a linear function of this stochastic variable nu t. Okay. And then using Ito's lemma, you can really check this one. So value of $1, value of $1. This is very intuitive. Value of $1 at dt time later is of course discounted value of that $1. We discount because we know risk-free rate is RT. So the price should be, and the time is this one, time difference is dt, here 1 day. So this is should be the price of the $1 at dt times later. Here, dt is 1 over 252, so it is basically 1 business day later. Here, nu t is the k-dimensional factor of state variable, like macro financial variables or other big data. So, or big data, possibly big data, to make it fun. So here, let's make a simple assumption for the purpose of class. So we have 3 sources of risk. Okay, only 3, not a big data. 3 macro financial value. I'm assuming only 3. So K equal 3. So dimension of this one, DV is 3. And then risk-free rate is 1% per year, which seems a lot. So I reduce it 0.1%. Okay. And then nu is random standard normal variable. So I generate K is 3 variable. And nu 0 is something we have to estimate. And then I just simply simulate it. Okay. It is something we have to estimate from data eventually. Again, as I told you, the whole purpose of asset price is to figure out this one. And the risk-free rate, we know the source of risk shock to the economy we can observe from macroeconomic data. The only part we don't know is lambda. And lambda, the only part of in lambda we don't know is nu 0 and nu 1, right? Because nu t is the data, macro financial data. So in this sense, the whole point of this affine term structure model is to estimate nu 0 and nu 1. Okay. So nu 0 and nu 1, and nu is lambda 0, and lambda is I simply model delta over here. And dz nu is, and then here, basically this one. I I simply assume this data. So I'm just assuming we know the data. So K and then this one. And then log of M, basically this part. So this part, I write down this part as RF risk-free rate dt lambda multiplication lambda divided by 2 dt and lambda dt nu. This is a log pricing color, and I exponentiate it to have a pricing color. And then simulated pricing curve is here 1 point something. Okay. If I do it again, I have a different number. Okay. So this is the review of the previous class.